Alrighty, hello. Let's get into it. The topic of today's video is collisions. Just a side note, it's a good idea to run through the start code before checking the rest of this. Head into the GitHub, link in description, because I have modified a few things. I found in switching to Python 3.10 that the mouse movement just went really horrible. Instead of moving continuously, the mouse would sort of jump in discrete steps. And the reason for that, I'm not really sure why why this wasn't causing an issue before, but it is now. Is basically when you get the mouse, when you call pygame mouse get position, it returns the integer position. And there's really, as far as I can see, no way to change that. I tried a few approaches. In the end, I switched everything over to GLFW because GLFW tracks the mouse position as a float, which means we get decimals, we get those in-between values, and we get a nice smooth mouse control. So yeah, do check into that. But let me just run this and show you the scene that we have right now. We have our environment, and I've generated a whole bunch of random blocks, but we're not doing any collision checking. So right now we can pretty much just move through all of it and nothing happens. So let's fix that. Also, it's important to note another thing that I've changed, which is sort of the process that I'm using here. So we can sort of close this all off. So we have our scene, create our objects. Okay, no problem at all. Now in the update, this is a little bit different. So instead of calculate jump, I'm sort of breaking the update into several steps. First of all, I perform any logic that I need to perform to calculate what an object's velocity should be. Then I perform sort of a move function, and this move function is not performed at the object level, it's performed by sort of a different level of abstraction where we have visibility of all the other objects that we could collide with, basically. Because how would this work? Player is a player class, and player needs to know about a block class, so player imports block, but block might move and might need to know about player. And this is a circular import. So to get rid of that, we just have it controlled by the scene. After calculating movement, we then sort of apply any tidying up operations that need to happen. And we're also keeping track of the position in the last frame so that we can get the camera movement, the player movement, more accurately without needing to return things from functions. So this is the TLDR here is just have a look through the code, make sure you understand it. Now, a lot of this is based on the concept of a block or a box. Now, if we look at player has a box object. And this box object tracks its position, more or less, and collisions can be performed with it. So the box object, is an AABB. That's an axis-aligned boundary box. So we can go here to geometry, okay? And at the moment we just have a box class. This is all that it tracks. Okay, let's add collisions. So we'll go to this geometry class and we'll make a function to test if this box is colliding with another box. Okay, so there are some weird cases to check for collisions, but there are also some very obvious cases. This box has a center, and the leftmost position will be the x-coordinate of the center minus half of the length. Now, if the leftmost boundary on the x is less than, let me do it another way, is greater than the rightmost boundary on the other object, then these boxes, no matter what the other coordinates are doing, they can't be colliding with each other. Okay. Now what we'll do is we'll do a whole bunch of these tests, and then if all of these tests go through just fine, then we can say, yes, these objects are overlapping with each other. So that's the leftmost boundary. We can then look at the rightmost boundary of our object, and if our rightmost boundary is greater than the leftmost boundary of the object that we're looking at, then yeah, no matter what the other ones are doing, they won't be colliding. So what we can then do is duplicate this a bunch of times, because the logic is really, it's still the same. So here we're looking at the, if we're viewing this top down, the north and south boundaries. So here we have the southmost edge is above the northmost edge of the other box. And likewise, the northmost edge is, oops, confusing myself. The northmost edge is further south than the southmost edge of the other box. And we have similar analogies in the Z coordinate. Okay, that is looking good. So we have a routine which will tell us if one box overlaps with another. Let's go back to the scene and let's use that. So before we worry about moving things, let's make a function called, here's my move function here, okay? Let's make a function called canMove. This takes, well, it's a class function. It takes an arbitrary object and it takes a velocity with which that object wants to move, and it tests if that's possible. First thing we'll do is create a, I'm going to call this a temporary box to represent the sort of the box that the player wants to move into. Okay, and we can get this by taking the dimensions of the existing box, as well as we'll take, so with the box, the center is a numpy array, which means we can just add them on, and we'll just make sure that velocity is a numpy array as well. Then we can say, okay, object box center plus velocity, and that will be the new position that we want to move to. Okay, so now what we'll do is we'll just test, so we'll say for block in self blocks, okay, great. Yeah, so we just test if something overlaps, and yeah, there we have it. Side note, I just realized looking here, we have a move player function. I just want to clarify this. In the previous video, the move player function was sort of setting the player's position automatically. In this video, in this stage, the move player function is really just here. It's really just setting the velocity. We've got a bit of other logic here. So if we're floating, then we add to the velocity. Otherwise, we reset the velocity. And this is because I'm just going to make it so that when the player's floating, they just naturally float forwards a little bit each frame. That's fine. And then in the update, I set the components of the velocity to 0 so that that can be reset in the next frame. It's just very rudimentary for now. Okay, so applying movement. Well, let's not do this. Let's save this and say this is the, if we take dt times the velocity, this is the velocity with which we want to move. Then in order to get smooth movement, even with collisions, I'm going to test each of the 3 dimensions of the velocity independently. So I'll make something called test velocity. And we'll just go ahead here. So we'll say if we can move, then increment our position. So we'll say, okay. And yeah, as we can see, we're just setting the incrementing the X direction. So I'm just going to sort of get rid of this for now. Oh, no, I'll leave that. I'll leave that. So we'll do the other 2 dimensions. Okay, so this third dimension is where things get a little trickier because we might be blocked in the Z direction, and there's 2 reasons for that. Either we're moving up, we're hitting a roof, or we're moving down, in which case you want to sort of catch the ground level below us. So now we can go, okay, otherwise, if the velocity that we're moving with is less than 0, then we're going to do some stuff. So we'll say, sort of send it to a stop and then indicate that it is on the ground. Okay, and then so this is sort of a collision with a block that's giving us a ground level, but we do also need to check a collision with the ground, which won't show up in this test up above. So if we're below this certain level, then yep, keep that. I'm actually gonna, I don't know if it makes a difference, but I'll just set that. Okay, so let's give that a shot. Okay, now you may notice that it's basically working, but it's not very good. It's too slow. And the reason for that is very obvious. We are checking against every single object, even those objects that we couldn't possibly be in contact with. So if we go back and we go to the canMove function, and I'll just go, okay, look through all the blocks and then set the color to make it clearer that this block has been searched. Okay, so every red block here is being searched. And honestly, it's, especially with Python, it's really amazing that it's even getting any sort of frame rate. So clearly this is not good. How do we fix that? Well, there's a technique, basically space partitioning. So imagine that we have an invisible grid cast onto this space, and the position that the player is on, rounded, divided appropriately, will give us a grid coordinate. And then in that grid coordinate, we can track all the objects there. Now, we could do this with an array, but it's a lot of grid points, and they're not all necessarily full. I mean, they probably are in this case, but in general, they may not be. That might be wasted space. Python has a data structure called a dictionary, and that's going to be pretty useful here. So I'm going to make a system where the key for the dictionary is a tuple of 3 integers, an x, y, and z index for a grid square, and the value for that given key is a list of all the objects which occupy that space, or just nothing. It might not be in the dictionary at all. So that means we can save a little bit on space, and yeah. So let's go and code this up. I'm just going to shift a few things right now. So we can go to... Now I'm just going to... I'll go back to this in a second, but I just want to simplify this scene because it's going to make it a little easier to visualize what's going on. So what I'm going to do is I'm just going to make a simpler set here. and we're going to work with that. So going to get rid of these move functions. Move and can move, get rid of those. Okay, I think that's fine. And then I'm going to sort of jump into geometry. Okay, so here I'm going to call this a grid. Okay, so we define the length, width, and height for the grid squares, as well as this blank dictionary of items will hold everything there, everything in the game world. Now, this grid is going to be a static class, which means we can instantiate it down below, and then we can refer to it from other modules as simply, actually, let me show you this. So if I go over to View, I'm going to make a general wireframe model to visualize the grid squares. So we can, I'm just going to copy paste this over. Okay, so this frame model here, wireframe model, will take a given length, width, and height. And here we specify 1 point and then the next point. And these are just all the lines that we would need to make a cube of this length, width, and height. So the way we can use this is we need to get the length, width, and height of our grid. And we can go up here, import grid, import geometry. And then down here where we, oh, this is getting messy, where we create the assets. Okay, so we want to get the static class, we want to get its properties. So we can go geometry, and then the instance within that is called grid, and we can simply pull out its length. And there we have it. So that's how we use a static class, for instance. What we'll do down below is we will actually render those grid squares, but if we render all of them, it's a little bit messy, so I'm not going to do that. What I'll do is I'll focus on finishing off the grid functions first, and then we can visualize those grid squares. So this is going to seem a little strange at first because we're going to have a whole bunch of little functions which don't seem to do much, but then we'll see how they come together. This is the magic of software engineering. So what I'm going to do is I'm going to make some conversion functions. So a function which takes the world coordinates and converts them to grid coordinates. Okay, then I'm going to go, oh, why is that complaining? There we are. Then I'm going to go back the other way. So I'm going to make a conversion function which takes a given grid coordinate and returns the world coordinate for the center of that grid. So yeah, the reason I'm adding 0.5 is because we basically want to be halfway into that dimension, if that makes sense. Okay, great. So our grid can convert coordinates. The next things I want it to do is to be able to add and remove objects at positions. Now remember, the grid object has a dictionary, and the dictionary sort of has sparse memory allocation, so it's not necessarily even going to exist. So we're going to have to do a few checks. First of all, we want to check if the coordinate is not even recorded in the dictionary. If that happens, no problem. Let's just return as if nothing happened. And then if that is in there, then we can access the list of objects for that coordinate by indexing it in here into the dictionary. So we put that in as a key. So the next thing we want to check is, obviously it wouldn't make sense to remove the object if it's not in that list. So if the object, we goofed up, the object is simply not in the list for that dictionary, no problem. Again, just return as if nothing happened. Okay. So if these checks sort of pass through and nothing happens, then the object is in that list and can be removed. So there's a function called remove, which simply takes the object and removes it from that corresponding list. And then if we have a coordinate where all of the objects have been removed from that coordinate, don't think it makes a big difference, but I am going to remove that from the dictionary. There might be a little bit of overhead there, but it is a little cleaner. Okay, so we're putting in the key name for the dictionary and popping that out, and that is basically deleting that entry from the dictionary. So great. Okay. Now the next step is, okay, can we add something to the dictionary? And this sort of comes down to two cases. Either we're adding something to a dictionary in a position which has already been seen by the dictionary, so there's a list sort of existing there to add into, or we're adding it completely new. So we're just adding it in a position where nothing has been added before. Slightly different. So the other check is if the object that we're adding already exists in there, that would make no sense to add it twice. In that case, we simply return, done. Okay. But if that isn't set off, then we can add it. So we can go self items, add that coordinate, append that object. So yep, add it in there. Okay. So if this is completely new, we can still sort of do this. We'll go self items, coord. Now, when we set this in, this actually creates the key, brand new. So we put in object, but we need to put it in as a list, and that creates the list that we are working with. Right, so we can remove things from our grid system. We can add things to our grid system. What's the next thing we want to check? Well, how would we add an arbitrary object? We would add the object, and the grid system would sort of need to sniff around and check which coordinate to add it to. Of course, we could simply take the object's world position, divide it, that gives us a coordinate block, and stick it in there. But what if, this grid system is a virtual set of lines. There's no reason that objects need to be entirely contained, and they probably won't be. So we should also have a system that takes a coordinate and sort of searches around and expands. So it's sort of like a flood fill algorithm. So this is the next step, is I'm going to make an expand function. And this is pretty messy, but we'll do it. Okay, so we're going to take a given coordinate and sort of explode that coordinate in all directions, also bearing in mind, the set of things which has already been searched, because we don't want to set up loops. So I'm going to copy paste this. This is really sort of messy and annoying. There are definitely neater ways to write it, but not necessarily more performant ways. Okay, so take the x, y, z coordinate, and then we check, okay, we'll expand left, so one step to the left on the x, one step to the right, one step below, one step above. We're just going through by hand all the different directions that we can expand, and only expanding them if they're not in the search history already. So again, I'll sort of leave this for you to sniff through. We could simply do like a triple nested loop. It would do exactly the same thing. But yeah, I'll leave that there. Okay, so now, next function, I'm going to call this get overlapping coordinates. And what this does is it takes a box and it sort of checks the first position, the most obvious position that the box would be in, and then it searches the grid system and says, okay, what's the set of coordinates in the grid system for the imaginary squares that hold that box? Seems a little abstract right now. So let's take this one step at a time. We'll get the world coordinate of our box. Okay. We'll get the grid coordinate for that. Okay. And now we'll start searching. So we'll have a number of lists. We'll have a list of things that we want to search. We'll have a current coordinate that we're searching. Let's set that to none for now. We'll have a search history, so a list of coordinates which have been searched. And we'll also have the set of coordinates which contain that box. And that's what we're going to return in the end. Okay. So we need to start somewhere. So what we'll do is we'll take the grid coordinate, which is a pretty strong chance that the object is within that grid coordinate. And then we'll say loop through. So we'll say while the length of the things we want to search. So while we still have something left to search. Okay, no problem. Just double checking. That's always good to check. Okay. Yep. So we get a thing from our list and we put that into our search history. Then I'm going to do a few other things. I'm going to get the world coordinate of that position. Okay. So what I'm doing is I'm making a box object which is going to represent that imaginary grid square. See, it's based on self-length, width, and height, centered around this world coordinate, which was based on the grid coordinate that we're searching. Hopefully that makes sense. Now, we're going to add this if this temporary box overlaps with the given box. So this box, for instance, could represent the player. We want to check if the player's box overlaps with the grid coordinate that we're searching. Okay, in that case, we save that coordinate because it has passed the test. And now what we'll do is if we've successfully collided in that grid space, there's a chance that we're going to collide in the neighboring grid spaces. So we'll go expand the current coordinate, taking into account the current search history. And we'll look through that. So we'll say for coord, in that. So I mean, a naive approach would simply be to search every single possible grid position and see which grid boxes overlap with the object. That's really bad. That definitely can't work in real time, which is sort of the goal that I'm shooting for. So we've got that. We can get overlapping coordinates. Now we're ready to make a general add function. Okay, so we're adding a general object. We know nothing about the object. What we can do is get the coordinates that it covers in our grid. and then we'll look through those coordinates and add the object to that coordinate. So a particularly large object or an object that's on boundaries can exist, can be registered with multiple coordinates within our grid. That is fine, because the purpose is just for collision checking. That's still reasonable. But then what we need to do is, I'm going to modify this a little bit. I'm going to go to the box object, and I'm going to keep track of its coordinates. I'm going to say, okay. After we do this, the coordinates of the box are these covered coordinates. And the benefit of that is then when an object moves, it will tell the grid system, hey, I'm moving, and by the way, I occupy these spaces. And then it will know how to check that sort of more optimally. So we're getting there. We are getting there. The next thing we need to do is have a function to check if a object intersects with anything. So this might seem a little strange. What we're saying is we have an object which is moving into this temporary box. So we haven't moved there yet. We want to move there. And it's currently in this coordinate, if that makes sense. So what we can do is we can say, okay, if we're moving into something which has no objects at all, then that won't even be in the dictionary. In which case, yep, this is definitely fine. Return false, we are not intersecting anything. Okay, now that out of the way, we can then loop through. So we can say for object 2. Now this is the reason that we need to pass in the object reference, because we need to check if something is colliding with itself. So which will happen. If that happens, then simply continue and look at the next object. Okay, now we'll go, oh yeah, good idea as well to set the other object's color to indicate that it is being checked. Just for our visual purposes to see how this algorithm is working. Okay, now we have the actual check. Okay, yep, so if any object collides with this, then return true, because we are intersecting something. Otherwise, yeah, we're good to go. Okay, so now we'll go back to the other two functions that I had before, which are can move and move. Okay, so we're asking the grid, can this object move with this velocity? So first of all, we'll grab its box. Great, and then we'll just check everything. Okay, so again, as you can see, this is the benefit of an object sort of knowing what its coordinates are, because then we have a small amount of things to check within, and then within each of those coordinates we'll have a small amount of blocks to check against. Right, so now we'll make the move function, and the move function is pretty much the same. As a matter of fact, I'll just copy paste the first part because it's exactly the same as the function that I deleted from scene. So, okay, can a given object move at a given rate? So for a given dt. Okay, so we take, calculate the velocity, we test each of the velocities individually. And I just realized what we should be doing what we should be doing is resetting the coordinates each time for maximum stability. So in my notes before, I was just testing this once, but I should really be doing it each time. Okay, so how does this work? So we go ahead, we shift our center, and then we get for the box's new position, we get the coordinates that it's within. This goes through the same function that we did when we added the block initially, but it's pretty efficient now. And then, sorry, then we look through the new coordinates that we're going to, and if we find one that we are not in already, then we add ourselves at that position, and then we look at the coordinates that we were in before, and if we find one that we are not in now, we remove ourselves from that position, then we reset our coordinates, our coordinate set. So we can sort of bring this together. A little bit messy, but there it is. Okay, so now let's go back to the model. And so we have the player. We'll go import geometry. Yep, we've got that there, okay. So we'll add player to the grid. Then we'll add the block to the grid. And this is done in the creation code. So now we can go to update. And all we need to change is we go geometry, grid, move the player. And that's it. So let's give that a shot. Let's see how that looks. I probably typed something wrong. Let's find out. Okay, so we go close, and we are only considering one block. Oy, that's not good. That's not good. Okay. Classic error. Classic error. Can you spot it? We should be comparing to the other object, not the self object. This is really... Well, that threw me. Okay, so again, let me go through this. Hopefully this has fixed it. So we sort of break this down into 3 independent movements. We perform the 3 movements, and every time we sort of reset our grid coordinates. Hopefully that makes sense. Okay, let's try that. Here we can move, yep, and we are being blocked. We can also jump up and onto things. It's not perfect. As you can see, we're sort of falling down into the block a little bit, but I'll look at that in future. So just so this really makes sense, let's visualize how this algorithm is working. So in our view, we have created a general block which will represent a grid. So we can go right down here and we can render these blocks. Okay, so we bind the VAO for that general block. We loop through all of the registered coordinates within the grid system. We get the world coordinate, set that as a model transform, and yeah, draw it in lines mode. So run this, and we can see sort of the grids that we're within. So here we're just within one grid. We can sort of be on the boundary of a few of them. It's actually pretty hard. And as we jump up, we're sort of checking a little bit above us as well. But as we move out of a position, that position is removed from the dictionary. So we're not storing heaps of space. Then we can see, okay, here we can see we are within an overlapping grid coordinate. So potentially going to check against that. Here we are checking against a number of blocks. And yeah. So yeah, it's pretty cool. We can go, and this, yeah, so we can go back to the scene and reset this to the really big random. Okay, yep, so we're resetting everything. Run this, and it will go slowly, and the reason for that is actually because we're drawing the grid coordinates, which is a lot. That's a lot. So let's just get rid of those grid marker lines. Just takes a bit of time to generate the random blocks. And now you can see performance before was about 30 frames per second. Now we're back to the regular 50 because we are only checking a small number of those blocks. Now you may find, no, this is okay. I'm happy with this. This is fairly stable. This could even be, it's not a good block distribution. This could even be a good little mini game. I'm not very good at it. Anyway, so point being, we have an efficient collision system now. That's good. I'm happy with that. There's sort of one more thing we can do, and sort of up to you whether you do this, but I think it's a good idea, and that is to be a little bit more informed about how we are expanding these sectors. So instead of just brute forcing it, we kind of will brute force it still, but just with a bunch of conditional statements. So we only want to expand a sector if the object's boundary exceeds that sector's boundary. So we can go over to the expand function and change this. So this is sort of checking everything by default. Now we can sort of speed that up a little bit by checking a bunch of conditionals. And this is basically just checking which boundaries of the object exceed the box and only sort of expanding those boundaries and just doing combinations of these. So if we go north and east, then yep, we're going to go northeast, northeast above, northeast below. This might speed it up a little bit, depending. We can run this. Oh yeah, we need a bunch of other things. We need box and temporary box. So if we go down to yeah, we can pass those in and see how this goes. And there we have it. Let's, oops, I fell down. Yeah, so as you can see, we are sort of falling into the block a little bit. That's not great. We can fix that up in the next episode of this series. But yeah, pretty cool. Pretty cool. All right, so there it is. I hope that was useful for you. Hope you had fun. I had a lot of fun making this system. It was very cool. Yeah, I'll see you again soon. Bye.